This final unit of our business calculus course is going to take a look at applications of derivatives and integrals. And usually we're going to focus on the context of business and economics. To start off with, though, we're going to do a general applications discussion for the derivative around this concept of optimization as we answer the question, how do we find the optimal decision for a given situation? And the answer to that we're going to look at first graphically, and then we'll convert it to algebraically what we're doing. But graphically, if I have some function that comes through like this, and I want to know what maybe the maximum revenue is, or maybe the minimum expense, what's unique about those 2 points is if we think about a tangent line that touches those points, a tangent line through those points will be a perfect horizontal line that has a slope of 0. Whenever the slope is 0, we know we're either at a local maximum point or a local minimum point. Let's actually notate that. At the min-max point, the slope of the tangent line also known as the derivative, is 0. That's going to be what we want to find in order to answer these optimization problems. What we're going to do is we're going to set the derivative equal to 0 to find the optimal point. So for example, let's say I'm making a rectangular garden. That is to be fenced in along a barn. With only 60 feet of fencing, what dimensions will maximize the area of the garden? That's the optimal point, giving us the most area. The idea here is we've got some type of barn, and along it, we're going to fence in a garden. And we don't know the dimensions, so we'll call it x by y. And actually, this bottom dimension then also must be x, which means if I'm talking about how much fencing I have, I see there's an x, a y, and an x. Put that together, we've got 2 x's plus a y of fencing. And we know we're limited by only 60 feet of fencing. This equation limits or controls how much I can have because it tells us the maximum perimeter distance around has to be 60 between the 2x and the y. But what we're interested in is maximizing the area. It's a rectangular garden, so it's going to be base times height, which is x times y. That's what we want to maximize. The problem is maximizing with 2 variables is difficult, so we'll use our limiting equation here in blue to help us reduce from 2 variables down to 1 variable. Y is the easiest to solve for if I just subtract the 2x. So y is equal to 60 minus 2x. And I can replace that y with the 60 minus 2x. And if I distribute, we end up with 60x minus 2x squared. That is the equation for the area. That is what we want to maximize. Well, to maximize an equation, we know we take the derivative, which is 60 minus 4x, and set it equal to 0. Adding 4x to both sides and dividing both sides by 4, I get that x has to be equal to 15. So one direction, coming off the barn, I know we've got 15 feet of fence. We still don't know the height, but the height is y. We can plug that 15 into the y equals equation to see what height we end up with. Y is 60 minus 2 times 15, which is 60 minus 30. So the y dimension must be 30 feet. And so the dimensions to maximize the area of my barn is 15 by 30 feet. And that'll give us the maximum area. Take the derivative and set it equal to 0. It's our general strategy. Let's try a problem in a slightly different context. Let's say the population of deer in a certain area is given by the number of deer at a certain point of time is equal to 500 plus 500t over 1 plus 0.04 t squared. What I want to know is when is the population maximized? Well, we know that maximum optimal point is going to occur when the derivative is equal to 0. So we'll find the derivative of our n function. We have a quotient, so we're going to use the quotient rule. Quotient rule says we take the derivative of the top, which is 500, times the bottom, minus the derivative of the bottom, which is 0.08t, times the top, 500 plus 500t. And we need to divide all of that by the denominator squared. That's the derivative, and we know the optimal point happens when that derivative is equal to 0. So let's look at solving this function to maximize the population. First thing I'd do is I'd multiply both sides by the denominator, the 1 plus 0.04t squared squared, 1 plus 0.04t squared squared, because that divides out the denominator, and anything times 0 is just 0. That's really nice. Then I'm also going to distribute. So we have 500 plus 20t squared minus 40t, continuing to distribute, minus 40t squared equals 0. And I'm going to, since we have t squareds and t's in this problem, let's combine like terms. So we have negative 20t squared minus 40t plus 500 equals 0. And ultimately, what we're going to have to do with this function is either factor it or use the quadratic formula. It's really hard to factor with such large numbers, but I do notice I can divide everything by 20. So I'm going to divide both sides by 1 over 20. And actually, I'm going to make it negative just so that the squared term is positive. So that's going to end up with t squared plus 2t minus 25 equals 0. And gee, that does not factor. So we do have to use the quadratic formula, which says the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so cleaning that up, we get negative 2 plus or minus the square root of 4 plus 100 is 104 all over 2. And technically, we have two answers here, one from the plus, one from the minus. But if I do the minus, negative 2 minus something is going to give me a negative. And we're not talking about a negative amount of time for this deer population. So we can probably just say negative 2 plus the square root of 104 over 2. And if I put that in my calculator, that's going to come out to 8.1 years. At 8.1 years, the number of deer seems to be maximized. Let's do one more example before I let you go to practice some of your own. This is a great example about pricing and how demand is adjusted by pricing. Because as the price increases, fewer people are going to purchase it. So how much do you charge to make the most money? That's the question that a hotel wants to know. A hotel can rent 200 rooms a day. At $80 per room. For each $5 increase, 10 fewer rooms will be rented. What should they charge? If they want to maximize the amount of money that comes in. Well, to calculate revenue, the amount of money that comes in, it's simply the number of things that we sell times the price of those things. If I sell 2 pencils for $3 each, 2 times 3 would be a revenue of 6. We just multiply the number by the price. Well, what do we know about the number of rooms? We have 200 rooms rented. But for every time I do a price increase, let's say x is going to be the number of increases. Every time I do a price increase, we get 10 fewer rooms. So I'm going to subtract 10 for every one of those increases. So 200 minus 10x is going to be the number of rooms I can rent. And at what price am I renting them? Well, initially, we're renting them at $80 a room. But we're going to increase in sets of 5. So we're going to increase $5 for every one of those price increases. Plugging that into the revenue equation, then, the number is 200 minus 10x. The price is 80 plus 5x. And we now have a function that we can use to maximize our revenue. To maximize the revenue, we know we take the derivative and set it equal to 0. This will probably be, we could use the product rule here, but this will probably be easier if I first FOIL this all out. So let's do that. 200 times 80 is 16,000. 200 times 5x is plus 1,000x. Negative 10 times 80 is negative 800x. And negative 10 times 5 is negative 50x squared. So putting that together, revenue is equal to, putting the negative 50x squared first, combining like terms to get 200x plus the 16,000. It's maximized at the derivative. So we find the derivative, which is negative 100x plus 200. Set that derivative equal to 0. Come over here to do a little work. Adding the 100 to both sides, we get 200 equals 100x. dividing by 100, x equals 2. So now we should be able to figure out, the question is, what should they charge? Be careful, x equals 2. They should not charge $2 per room. We've got a function that says the price is 80 plus 5x. So we want to make sure we answer the correct question. The price is equal to 80 plus 5 times the x that we found was 2. So the price is 80 plus 10. They should charge $90 per room in order to maximize their revenue. So today it's just kind of a general application of derivatives, finding that optimal situation that either minimizes or maximizes a problem. And we simply find that minimum or maximum point when that derivative is equal to 0, because that's where the tangent line is going to be flat. That's the mountain or the peak of the function. Try a few of these, come to class prepared with questions, and we'll go from there.